All right, I want to say one last thing about this example, and that is I'd like to take the information in this SVD and address the concerns about compression or the idea of compression. So compression. So the idea behind compression in this context says that we can take the information inside of A and sort of package it differently according to the singular value decomposition. So in this singular value decomposition, we're defining a few different components, and I think it's worth labeling everything here. So in our SVD, we have a few different important parts. First of all, we have the actual singular values. The first singular value is root 10. And the second singular value, sigma 2, is equal to 2. Then there are the columns of u. And the columns of u here are the two vectors, maybe u1, which is, everything in this first column is scaled by 1 over root 30. So I'm just going to factor that out. And then this is multiplied by -1, -5, 0, 2. And then u2 here, everything in this column is scaled by 1 over root 6. So I'm going to factor all those out. And this is multiplied by -1, 1, 0, 2. And then we also have the columns of V, which are the same as the rows of V star here. And keep in mind, everything is real. So I'm not actually conjugating when I write this notation, but I think it's good to get into this habit in case we ever do bump into something that's complex and not real. So we have our two columns of V. V1, so everything here is divided by 1 over root 3, or divided by root 3, so we're factoring out a 1 over root 3, 1, -1, -1. And then we have V2, which is everything here is divided by root 6. And then we're scaling by 2, 1, 1. So now the idea is that we can take this information and use it to write our compressed sums. So we can write our full compression. So our so-called compressed sum is, well, we know that our matrix A, which let's remind ourselves what this matrix is, -1, -1, 0, 2, and then 0, 2, 0, 0, 0, 2, 0, 0. This matrix is equal to a linear combination of two rank 1 matrices. We have our first singular value multiplied by the first column of U multiplied by the conjugate transpose of the first column of V. And then we have our second singular value multiplied by our second column of U multiplied by the second column of V, where we conjugate transpose. So if we take the data we just wrote down, so if we plug in sigma 1 equals root 10, u1 equals that vector, and then conjugate transpose v1, and then we add sigma 2 equals 2 multiplied by the second column of u, and then the conjugate transpose of the second column of v, we end up with an equality. So what does this actually look like? Root 10 multiplied by the first column of u, which is 1 over root 30 times the column 1, -5, 0, 2, multiplied by v1 conjugate transpose. Everything there was divided by root 6. So we're multiplying here by the row, everything there was divided by root 3. So we're multiplying by the row 1, -1, -1. And then our second term here is sigma 2, which is 2. Then we multiply by the second column of u, which was 1 over root 6 multiplied by -1, 1, 0, 2. and then multiplied by the second column of V conjugate transpose. That's everything there is divided by root 6. And then we have our row 2, 1, 1. So here what we're doing is we're taking the data in A, and then we're expressing it as a sum of singular value times column of U times conjugate transpose of a column of V plus second singular value times the second column of U times the conjugate transpose of the second column of V. So this is actually an equality here. These are equals signs. And again, note here that A has rank 2. The last thing we can do here is we can find what's called the rank 1 approximation. And what this says is that our matrix A is not equal to, but it's approximately equal to what we get when we drop off the second term in our compressed sum. So if we just ignore this second term, we'll be left with one rank 1 matrix. So here we'll be looking at sigma 1 times the first column of U times the conjugate transpose of the first column of V. And that's equal to root 10 times 1 over root 30 times 1 negative 5 0 2 times 1 over root 3 multiplied by 1 negative 1 negative 1. And let's see if we can't multiply this out. Well, actually, when I multiplied it out, here's what I got. I got, let's see here. Well, I think we can do this together, actually. So I have 1 divided by root 30, 1 divided by root 3, and then that's in the denominator. And then in the numerator, I have root 10. Well, root 30 is root 3 times root 10, so the root 10 cancels, and I'm left with 1 over root 3 times 1 over root 3. So really, I just have a factor of 1/3. And then when I multiply this column by this row, what do I get? I get 1 negative 1 negative 1, negative 5 5 5 0 0 0 2 negative 2 negative 2. So this is a rank 1 matrix, which is definitely not equal to A, but this is considered to be a rank 1 matrix that approximates this A. So this is sort of like a much smaller example, analogous to the cat picture I showed in the video. Imagine the cat video I showed in the video as having being a grid of data that was our original matrix. Well, the original matrix had a large rank, and so what we did to compress the data inside of that matrix is we calculated an SVD, and then we started dropping the terms from the SVD to look at lower rank approximations. The lower rank approximations for a very large matrix takes less data to define, which means that we're saving disk space. But as we saw in those examples, when we dropped too many terms, we started to lose too much quality. So that's it. That's our example for singular value decomposition. This full example is typed up and on the website. And there's actually a second example there too, which I'm not going to go through on paper here, but I encourage you to work through yourself. The example is very similar, except there is an extra step where when you go to find bases for the eigenspaces, you will need to apply the Gram-Schmidt step to one of those eigenspaces. So there's a tiny bit more work there, but I think it's worth doing on your own. I hope you enjoyed these videos. It's been a weird end of the semester, but I at least hope somebody gets something out of all this work. So hopefully I see you in office hours sometime soon. Goodbye.